All right, this is What's My Curve? This is JV Statistics. This is section 2.3. It's actually chapter 8 in the JV Stats book. We are doing, amazingly, a one-day lesson on non-linear regression. Can you imagine non-linear, what that encompasses? That's like saying a non-tiger. What kind of animals are non-tigers? That would be in just tons of different things. So when they say non-linear regression, I mean, you are talking about an infinite number of things you could put. I just have some classic ones that are located on the calculator. That's all I have. And a lot of them run similar, but you see the cubic one. We're used to the cubic one doing this, that S deal, right? You could have quadratic stuff, right? And you could have quartic. If you remember quartic, Quaartic, that's like a W, right? You could have a fifth degree polynomial, a sixth degree. You can have squared, cubed. It's unreal what you can have. And for the most part, when you're looking for patterns, most people use a little more highly developed software than what's available for us at this point. We'll be pretty much sticking to just a few, but just keep in mind, these are just some of them. There's tons of them. But we're going to analyze it in a pretty simple way, pretty much by R squared. Okay, we're going to talk about that as the analysis tool. So again, as I always say, stop the video anytime you need to. And check it out, go backwards, whatever you got to do. And I'll be going through the calculator stuff as well. And the calculator stuff takes a little time even for me to input it. So this lesson will take a while, but it's worth it. Again, it's why I record some of them that I think are a little more tedious that need me to do it this way. Okay, so exponential, you guys know exponential growth and decay as a good example of exponential growth and decay is, of course, we've seen things like the coronavirus over the years, or just pandemics that can affect people, and it could grow exponentially. This is a good example of the exponential decay of my vertical jump as I've gotten older. For example, power ones are similar, the quadratic ones. Sometimes in the quadratic ones, you use only just part of it. You may just use actual part of it. You don't use the whole thing oftentimes. And cubic and logarithmic, and these are all have exponents, the quadratics of power. They're all so similar. They have these names, but really the equations is what you're looking for. Then all of these are pretty much generated with software. It's not like you're going to go out looking for these by hand. It's kind of nice if you have a general idea of what it might be, because if you have a general idea of what it might be, I think you can more easily identify which way to start looking. Okay. All right. So construct these models. Okay. Step one is you're going to enter the data into L1 and L2. And I'm going to show you all that. Again, you want to write this down. And then stat calc, and then you could pick one of the following. These are all listed on the calculator. All of these should be listed there, okay? And there's other one. There's the line of regression too, which we've already done in previous lessons. Okay. So for the first one here, what I'm going to do is we're going to put this data X and Y. We're going to graph it, and then we're going to look at it. And then I have these three models, and you're going to see them. It's pretty simple how this is going to work. It's just time consuming. Okay. So let me slide this over to the other screen, which you can't see, but I can. And so I'm going to go to my calculator. We're going to go stat calc. Oh, sorry, stat edit, right there. Hit enter. You got to have L1 and L2 available. I'm going to put X is L1, of course, and Y is L2. Of course, I better type it in right. That would be very helpful if I actually did that. So 11.5, enter. 13, enter. 3.5, enter. 8, enter. 5.5, enter. 10, enter. 4, enter, 9.5, enter. Okay, I'm not going to sit here and do that on camera. I just wanted to show you that once, and then you're going to slide over to L2 and enter the Y numbers. And so I'm going to pause the video just for a second, and then I'll come back. All right. Okay, I am back with the data in. Okay, so once you get the data in, the first thing we're going to do is we're going to just go ahead and graph it. Okay, so when you graph it, go to second y equals and make sure all the plots are off, because sometimes that causes problems. Mine are all off. Okay, and then we're going to go to regular y equals and make sure everything's out of there, which I got to take that out of it. Get that out. Okay, great. Now we're going to go second y equals, back to that. I'm going to turn plot 1 on. See that? And I'm going to do a scatter plot, which is right where it is, flashing. L1 and L2 is X and Y, no problem. I'm going to go zoom and then the number 9. And that'll send. Now, what does that look like? Does that look linear? Kinda. It does. Does it look like it could be a power or an exponential model? There's a slight curve to that. Could be. So what we're going to do is we're just going to take some guesses at this. And the 3 guesses that I have are going to be the linear model, the exponential model, and the power model. And what we're going to do is we're going to evaluate which one's best based on which one has the highest R squared. Okay, so let's talk about R squared a second. R squared, which you already learned, okay, is a percentage. It's the percent of variability in y due to x. It really means what percentage does the line take in of the dots of the variability. So the closer you are to 1, the better. Now R is only for a linear concept, but R squared is a measure for every single model. Okay, and how it's calculated is done by software. It's not something we're going to cover here. Okay, so here we go. So I'm going to do a line first. So I'm going to go stat calc 8. Remember stat calc 8, that's linear regression. I got L1, L2. I'm going to go calculate. All right. And you got R squared and R. So R squared is 0.972, 0.97. Pretty good. It's pretty high. And there's my equation. I'm going to go ahead and write that down. So if you're looking, I'm going to slide this back over real quick here. And you can see you're going to go ahead and write down that linear model right there. And you're going to write down the value of R squared. And the one with the highest R squared is going to be the one that we think is the best fit. Okay. So great. Now what I can do if I want to, and I will, by the way, if you don't know how to turn on, if your R squared and R do not come on, let's check that out. Okay. So go second catalog, which is the 0 button. And then you're going to go down to diagnostic on. It's a D's, diagnostic on. Okay, which is right. Diagnostic on. Okay, and you're going to hit enter. Okay, hit enter again until it says done. And now your R squared and R should come on. Mine was already activated, so it was ready to go. All right. So I'm going to go to y equals, and I'm going to put that equation in here. Okay, what I just did. And you can type it in by hand, or the calculator will save the last regression equation you did. Let's check it out. Okay, so I'm going to go vars. I'm going to go down to statistics. Hit enter. I'm going to arrow over to equation. And that's my last prediction or regression equation that's been saved. Hit enter, and it's in plot 1. I'm going to go ahead and just graph it just to see what it looks like. Okay. All right. Does it fit? Pretty good. Could be a little curve going there. Okay. Let's go to the next one. Okay. So let's go stat calc. And this time I'm going to do an exponential model, which is what I have underneath question 1A on your notes. And the exponential model is right here. Okay, let's see what this does. Okay, L1, L2. And let's see if I can get an R squared higher than 0.972. I did. I got I think I did. Yeah, I got 0.9. No, it's really close. 0.971. Very similar. 0.971. I'm going to go ahead and write that down on your notes, the equation itself using the formula here. Okay, I'm going to go ahead and graph that. You ready? Y equals. I'm going to slide down to Y2. Okay, I'm going to go vars, statistics, number 5, arrow over to equation, and then regression equation. Okay, I hit graph. Okay, does that fit? It's okay. It's not great. Okay, all right. So I've done 2 of them. Now let's check out the power model. Okay, stat, calc, and let's go to the power model. Okay, see what that looks like. Power regression. L1, L2. Hit calculate. Look at that. I got an R squared of almost 1.9998. That's pretty good. Okay, and there's the model. Okay, so I'm going to go Y equals, go down to 3 right here, vars, statistics, equation, regression equation, hit graph. And look how good that black line fits the data. So I found the best data. You can see it visually, and then you could, it's also is very evident in the R squared value. So let me slide the notes back over so you can see those, okay? And you can see what I'm talking about. Okay, so that power model was the winning model, and it almost took in 100% of the dots. So 99.9% of the variability in Y was due to X, the way we had it from the third. So that third model is the best model, okay? All right, the next equation, the next one I'm gonna do is 1B, LQ basketball tickets available, time be at a certain time 0 all the way up to an hour and 20 minutes. Okay, a big game's coming up and the gym holds 2,000. So when they first go on sale, we got 2,000 tickets. But eventually, after a couple of hours, 115 minutes, we're down to 260 of them. And you can see the models here. We're going to get to those in a second. We'll check out which one's the absolute best model for this. Okay, this will be kind of cool. So I'm going to hit pause for a second, and I'm going to get everything set up for us. All right, and you should be typing time into L1 and tickets available into L2. All right, hold on. Okay, so for question 1B, LQ basketball ticket availability, I've typed the data in. Okay, I'm going to graph it. I'm just going to hit zoom 9. Okay, looks fairly linear, so that might be the winning model. So the 3 options that I had are linear, exponential, and I was going to do a kind of a quadratic model just to see, because I wonder if it's like part of a quadratic. I don't really know, but I'm going to check it out. Okay, obviously I messed around with these models beforehand, so I kind of know. So all right, so let's check this out. Stat, calc, and number 8's our linear one. Okay. And so I'm just going to go ahead and go down there and hit calculate. All right, so there's the equation. You can go ahead and write that down and write down the R squared value of 0.9988. Pretty good, or 9, somewhere in there, 98, yeah, 99888. Okay, I'm going to graph that, all right? Y equals, I'm going to go vars, statistics, equation, regression equation. I'll hit graph just to check it out. It looks, I mean, a linear model is a pretty solid idea. R squared is almost 1, and nothing wrong with that. All right, let's do another one. Stat, arrow over to calc, and I'm going to go down to the exponential model, which is down here a ways. There's natural log. I didn't do ln, but there's a natural. There's all kinds of things you can do, okay, to guess. Most of the time, it's just guessing. You're just kind of guessing and trying it out. All right, so we hit calculate. And that R squared model is 0.923. That's a little, it's not quite as good, but let's go ahead and graph that. And again, you can write that down. That's great. So Y equals, go down to number 2, vars, statistics, equation, regression equation. Whoops. Yeah, I got it. Yeah. And hit graph. Yeah, it doesn't, the line is much better. Even though it's a pretty high R squared, the line is much, much better. Okay. Next one, stat calc. I'm going to try a quadratic. I checked it out earlier. It doesn't look like a quadratic, but it's a real kind of a shallow quadratic. I just happened to look at it ahead of time. I already know kind of the answers to this. So look at that 0.9988. It's really high. It's really super high, the quadratic, okay? But look how tiny the a term is in the ax squared term is. It's really tiny. It's almost not even there. It's almost linear if you think about it, because that a term is almost 0, which would eliminate that, but that's fine. So go y equals and go down to C, bars, statistics, equation, regression equation, graph. Yeah, the black line and the blue line are almost the same thing. Okay, fine. So let's bring back in the answer key so you can pause the video and check it out. All right, here's the answer key. All right. You're going to want to pause that. So really, which model's better, the linear or this one? I would probably just pick the linear model. That's probably good enough. I don't think you need anything else, okay? All right, we're going to go to C now. And C, I don't have any context with it. I just have an X and a Y. I don't have anything there. And so I'm going to go ahead and pause the video, and I'm going to type in C so that we can do this. Okay, sound good? Okay, we're on 1C now on the notes. It doesn't have any context. I don't know why I didn't make anything up, but I have a linear, an exponential, and a power model to do there, okay? And we'll check it out. So let's, first of all, let's graph. Let's go zoom 9. Definitely doesn't look linear. There's no way that's linear, but I'm going to go ahead and do the linear model anyways. Stat calc 8, L1, L2, and go ahead and hit it. Calculate, and you have a very weak R squared of 0.5992, 599 or whatever, however you want to round that. So you can go ahead and write that out. I'm going to go ahead and put that on the first one. That's bars, statistics, equation, regression equation, graph. Okay, it's not linear. It's simply not linear. We can get a better R squared than 0.599. Okay, let's try another one. So stat, calc, and let's go over to exponential, all right? Okay, exponential, L1, L2. Now we got action here. This is 0.999. That's pretty good. It's a pretty solid. It does look like an exponential decay function, just what I pointed out at the top of your notes. It really does look like that. Okay, bars, statistics. Oops, let me go to y equals first. Go into y2, vars. Now try vars, statistics, equation, regression equation, and then go graph. That's a pretty darn good fit. I mean, that's really good. We got almost 100% of the variability accounted for. I mean, that's as good as you're going to get. I mean, you can get 100% of variability accounted for. You can. That's pretty good. I don't have to look much further, but I'm going to go ahead and do a power model, right? Stat calc, I'm going to go to power, which is somewhere right here. Power model, L1, L2, calculate. And that one, R squared is 0.8779. Go ahead and get that formula written down, or wait for me to bring back the equation. I don't really, doesn't matter either way. All right, so I'm going to go to y equals, go down to y3, bars, statistics, equation, regression equation, graph. And the black one's pretty good, but it's not as good as the red line. The red line's clearly better. Okay. So we got the winner on that one. So they bring the notes back in, okay? And you can see, bear in mind that the R squared value for this one got typed down there by accident. But you get the idea. The linear model is not good. This is definitely the winner. The exponential model is the best one. Super high R squared. We almost got all of variability accounted for, okay? All right, the last big one to graph will be the height of a rocket after blast off in minutes. Okay, minutes, and then the height of it, and that's in kilometers after blast off. All right, let's check this one out. So let me pause the recording to get everything set up for you before we do 1D. Okay. All right, so here's the data in there. I'm going to start with a linear model. Well, first we graph it. We graph that. Doesn't look linear. Definitely has a little bit of a, let's see, it looks exponential to me, but okay, I'll do linear. I always start with linear. Okay, stat calc 8. And you know, the R squared is 0.861. It's not horrible. It's all right. 0.861. It's not bad for the R squared. You can go ahead and copy down the equation. That'd be great. Okay. Once again, I'm going to graph it. Bars. Statistics number 5. Equation. Regression equation. Graph. All right. Definitely the blue line just doesn't look linear, but it's not horrible. Okay. Do the next one. Stat. Calc, I'm going to go exponential. I really think it's exponential. I think you know that too. Okay, exponential growth and decay. All right. It makes sense that a rocket would get going, you know, minutes after blast off, the speed would pick up. It makes sense to me. Okay, hit enter from what little I know about rocketry. But sure enough, R squared is 0.9988. 0.9988. Okay, that's a good one. Okay, I'm going to graph that one. Y equals, go to Y2, bars, statistics, equation, the last regression equation, which I just did. And yeah, that's that. The red line's really a good fit. Okay, had a high R squared. The last one's a power model, stat calc. The power model right there. Got L1 and L2 sitting there. All right, and that R squared is okay, 0.9203. It's all right, but it's not great. Okay. Y equals, I'm going to go to the third one and graph it to see how it looks. Bars, statistics, over to equation, hit enter, and hit graph. Yeah, the black line's okay, but it really misses that last dot. If you see that, it really misses it. So the red line is, of course, the win. What's neat is the visual winner is also going to have the highest R squared. It's kind of nice when the math matches up to common sense. That's what I always like about this stuff. Okay, let me bring the notes back in, and you can get a copy of all those. Keep in mind, let me move my mug out of the way here. Keep in mind that the R squared is down here for this guy. Again, a typing kind of issue there. And we liked the exponential model the best. All right, sound good? There's a lot of other ways to do, there's just so many techniques, old ones and new ones, to figure out what the best fitting model is. But the art of regression, and again, regression is a funny word because we use regression like to return to a childlike state. But when we mean, you know, mathematical regression, we mean prediction analysis. Okay. All right. So now we're going to, for the most part, you're going to do this on your own. You really don't need me to do a whole lot of this, but let's check it out. Okay. See the regression models for 1A. So again, have 1A in mind right here, these models right here in mind, okay, which I should circle for you. Have these in mind, okay, when we're doing these questions, okay? So what you're going to do is, it's just this is just calculator. So it says solve for the indicated models. Now, from exponential model, probably find y hat for x is 17. What y hat means, y hat literally means, the hat means predicted. So find the predicted y for x of 17. So all you're going to do is put in 17 for the exponential model. You're going to put 17 in for x right here. That's all you're going to do. Okay, this is just a plug and play thing. There's nothing for me to really go over very much. Okay. And then from the power model, find the predicted y for 17. You see how different they are. And then find x for y hat of 500. So put 500 in for the y and solve for x. And then from the power model, do the same thing here. So I'm not going to go through these because this is just literally, I think it's a question of you having the answers in front of you and you just plugging them into your calculator. Okay. So I'll leave that. I would stop it here so you can get the 2A for regression model 1A and 1B, the questions that we have here. Okay. And then here's for C and D. Again, I would pause the video and get C and D, okay, from these different models that we have above. So it's this is a little time consuming for you to sit there and plug them into your calculator and check the answer, but that's pretty simple, okay? All right, so let me move forward here, okay? Item 3, understanding the key features of the non-linear models. Okay, just a couple just little notes. If you remember, a linear model has a steady rate of increase. So you're adding a constant value. It's a slope idea and it's arithmetic. If you recall that from probably, that might have been algebra 1 actually, where slope is that constant rate of change, which is just adding a number each time. Exponential growth has to do with multiplying or dividing by a constant coefficient. And that's often called a geometric series, if you recall that. Again, this is not stuff that really shows up on tests, really, for our class, but I'm just trying to be thorough. And the power models are based on, ratios, areas, volumes. It could be all kinds of things, squared, cubed, all kinds of stuff. So again, most of this stuff for the purposes of this class is fairly trivial, but I'm just trying to give you some way of evaluating something by just looking at it. You can do it on a graph too if you have a good understanding of your all your functions. Okay, function recognition becomes pretty helpful here. You probably hear that in other classes too. Okay, so let's look at 3A through D. And it says, look at each table of values, a value, and determine whether the relationship between the variables is linear or an exponential. All right. I think in 3A, it's going to be linear because if you look, there's an increase of 20 for every x increase of 5. So it's just a constant rate of change. That's for A. For B, you have a multiplier by 3. For every x increase of 2, you have y's being multiplied. So that you have an exponential function there. For C is also exponential for a very similar reason, except the multiplier is 2/3. And then D is linear because y is increasing or decreases by -90 for every x increase of 2. So it takes a while to see that. I think if you actually graphed 3A, B, C, and D, you would clearly see which ones are linear and which ones are exponential. But we did that in the exercise above. Okay, again, just some things just to get you thinking about stuff. Okay, I'm really doing overkill here. All right. Now, the last one we've kind of already done, but it's kind of cool, okay? Which of the following models was the most appropriate? And that's what so I'm going to go back up here to all of these, okay? And it's pretty easy to figure out. So for question A, which one was most appropriate? Where you just simply going to pick the one that has the highest R squared every time. So that's the most appropriate. And you saw it when I graphed it, how well it fits. And again, on this one, it's almost a tie. If I remember, these two are kind of tied right here. For the linear model and the power one, there's all kind of the same. I'd probably go with the linear one in B, okay? Because it's just easier. And then in C, clearly this model was excellent in C. The exponential model, remember that thing fit almost perfectly, if you can recall that. That thing is absolutely perfect. Boy, 999 is almost 1. And then, of course, in D, that was also another exponential one. Okay. All right, that's a long lesson. This area is not heavily tested in the JV Stats class. It's lightly tested in the AP class. It's not heavily tested. Because what you're doing is you're taking literally a semester worth of classes, There are classes on nonlinear functions, okay? You're taking the entire semester. I'm doing it in one day. I mean, but it's a good quick hitter. I like that I videoed it so you can stop and go back and forth. All right, until next time.